Okay, welcome. And what we're going to do in this video is go one step further in explaining how slicing works in a general way. Okay, so I drew this picture, and so let's say we have a solid. This is an irregular solid, so it doesn't have a constant surface cross-section. Okay, so you can see that it gets thinner as you move down the x-axis. So what we want to do is, in a lot of cases, well, in this case we're going to start by, we want to find a cross-section that is perpendicular to the x-axis. Okay, now this may not always be the case. In some cases we may want to take a cross-section perpendicular to a different line, let's say the y-axis. And so this is going to be important for later on, because how you choose your axis is important, because if you choose the wrong one, your calculations can become very messy. So usually one way versus the other is a lot easier. Okay, some cases it's the same, it doesn't really matter, but again it's important to realize. So, but in this case we're going to start with the x-axis and say, hey, we want to create a perpendicular plane, right, our cross-section perpendicular to the x-axis. Okay, so now, in this case here, what we did was we took this solid and we partitioned it. We took several slices of it, right, perpendicular to the x-axis. Okay, and so here's the idea behind what we're going to do. So we split up into these solids, and what we're going to do is we're going to partition into a set of points where we're going to have these points from A to B. So here's our closed interval from A to B. And so we're going to partition the interval into subintervals, right? Just like we did with the area. And what we're going to do is we're going to pick a point, so let S sub I represent the slice stretching from x sub I minus 1 to x. So S1 represents this slice here, S2 represents this slice here, and S3 represents this slice here. So in my example I have 3 slices, so n equals 3 in this case. Area, we're going to let area represent the area of the cross-section located at a point x. For example, we're going to look at a cross-section here. Okay, but what we're going to do is we're going to let x sub I star represent an arbitrary point in each subinterval. Now it could be the left end point of each subinterval, it could be the right end point, it could be the midpoint, it could be any point, but we're just picking an arbitrary point within each subinterval. And that's what we're going to use in our area. Okay, so why? Because this is, we're estimating. So we're going to pick a point along the x-axis here, and then we're going to calculate the surface, the area of that cross-section at that point. And we're going to basically use, we're going to pretend that this is a cube or a rectangular prism, right? So there's a little bit of error. Sorry, haven't had my coffee this morning yet. Okay, so here's what we're doing. We're going to use a formula, right? So how do we find the volume? Excuse me. Well, from each one of these points is delta x. Now again, I did not draw my picture well, but these are the changes in x. And again, when we subdivide, I'm assuming all of these are equal lengths. So again, forgive my drawing, it's not the greatest. So this is going to be delta x, and then of course at some arbitrary value, x star, x sub I star, we're going to basically have the cross section here, right? So this would be where we would do our cross section. And we would find the area of that cross section. And so how do we find the volume then? Well, we're going to find the volume by using our formula of A times H. But in this case, we're going to use A of X star, where A represents a formula for finding area. Okay, whatever that formula turns out to be. So we're going to say A is area function evaluated X star, X sub I star, times H, which H in this case is going to be our delta X. That's going to be the other dimension. So that's going to be what we're going to use for one slice. Okay? So, but we have many different slices. So what we're going to do is we're going to take the volume of each slice based on this formula, and we're going to sum them up. So this, let's call that V sub I. So we're going to say volume is equal to the sum of I equals 1 to n of the formula X sub I star, A of X sub I star, times delta X. Okay? So in this case it'd be 1 to 3. And so of course if we take the limit of this thing, right? So again, if we take the limit of this thing, so we take the limit as n approaches infinity of the sum of these slices, that's where, the integral comes in. And so we get the integral from A to B, right, because this is on a closed interval from A to B, of what? A of X times delta X. And so that's how we're bringing integration into this. Okay, so we're going to do another example, and we're going to start building this in and start actually calculating simple shapes based on slicing, and then we're going to go from there. Have a great day.